So yeah, I run it. Well, so up here, if we're in the model view and we go to tools, right? We have this little model check, which is helpful because what it does is it says what kind of continuity do we have between nodes and elements. And look, the following nodes are not connected to anything, right? We can go and we can find those nodes. One very helpful tool, if you're in the model view or even the results view, is this find tool, right? So it associates, right, or grabs all of these known elements within your model and isolates them. So then you can go through, and if you said, okay, node 21 is not fixed to anything, or if you click on this, it highlights it in the view. It allows you to, opens up this modify tab, it's free, and you can fix it, right? If you wanted to isolate and look at, okay, well, what are all the nodes that are free? Well, all of these nodes are free, right? And it shows you these meshed nodes. Well, these are created nodes based on the fact that we have this area and we decided to mesh it.
If you have a free node in between two rigidly connected beams, is that satisfied? I guess
Yeah, because it's connected, right? There's stiffness associated with the degrees of freedom of that node because it is connected to elements.
I guess I was thinking more about what we were saying the other day, how you could either like fix the node or you could do rigid connect on both of the members going into that node.
Well, so that's different, right? Because fixing the node fixes it in with respect to space, right?
Yeah.
If it's fixed with respect to a element, right? Because right now, like if we looked at this node up here, right? This node I just pinned in the two like planned directions, right? But as it relates to rotations or vertical displacements, it's based on its connectivity to this element. It's going to chase this element. This element's going to give it the stiffness.
Okay, so if an element is free from the node, then it can, so it can separate, it can displace away from that. I guess
Yes, it could. Like there's no connectivity to it. So like you can under the
Still connected to node.
it might not be though. Like if it depends on the releases you put, Aaron. So like if you put in, right, you could release everything. Right? Each one of these is a degree of freedom, right? So you have your 3 translational degrees of freedom, which they just relate to the local coordinates of the member, right? Which would be our axial, our shear, and our both directions, right? That'd be our U and our V, and then our X, right, along the axis.
Yeah.
Okay, so you could release the ability for this element to transfer forces between it and its node, essentially. So like if this node, right, if I didn't fix it in any directions and I decided to release it in every direction, there'd be nothing holding this node, right? And there'd be nothing holding this member either. Is that mind blowing? Blowing minds.
Because I always think of like the element and the node, they're the same. I don't know, they're like together. I don't know.
Well, because like Amanda made a good point on Monday. You know, we're looking at complex models where there are multiple elements framing into a member. And so what this allows us to do is specific to an element, decide does its stiffness affect the node or not, essentially, right? Whether or not it can transfer forces between the element and the node. And you can over-release it, right? You can make it unstable because you could essentially provide no ability for this element to be attached to this node, and if the node doesn't have any way of holding it, then it's just floating off in space. Okay.
So on your footing model, if you wanted to model that instead of as a fixed footing, how with all the plates do you model the pin for the actual footing itself so that it can rotate, you know what I mean? Versus having the whole footing itself.
You mean like translationally?
No, well, no. 'Cause
Like if you
trying
want,
to
if you're
model-
saying like Norm Hall, the base plates are fixed.
Yeah.
So you're
Versus
saying
a
how do I
pin-based
model
plate.
that?
How do you model that with a bunch of plates versus like just a big, like I guess
I mean, why model it with a bunch of plates when if you're trying, like, we're gonna get to that, but like the whole idea here, right, is you're
You don't
trying to
need to-
model what you're trying to get out of it.
Okay.
So it's like if you're trying to model moment frames and you're fixing the base plates, right, where the columns come in. So in this case, we look at, and we're getting I was just trying to give you a little bit of intro here on this. So we're gonna say, right, this is a moment frame,
Yeah.
and I fixed the base plate.
Yeah.
Right? This would be, if I was designing the columns and the beam for this moment frame, and when I was designing this moment frame, I said, hey, I want the base plates to be fixed. This is the model I would make.
So why do you have a footing one?
Because the footing one, I was saying, okay, what if I wanted to design like the bearing pressure underneath this footing for the axial forces in a building that has gravity columns in it.
Okay.
So no transverse loads, just vertical loads, right? What it allows me to do is take into account the fact that the soil has stiffness to it, right? It has a K. You guys remember soils? Do you remember K factor? Pounds per cubic inch. It's this guy right here, right? So what does it do? If I'd hit this, we can generate plates, right? And we can create soil springs. What's the soil springs allow us to do? Well, it allows us to use a subgrade modulus, right? 300 pounds per cubic inch is a pretty good subgrade modulus, around 150 to 300, okay? So what does it do? Well, it goes through and says, okay, each one of these areas is a certain area, right? And that area, based on its displacement to each of its node, right? It would give each one of those springs a stiffness. And so then once see, it's not gonna run because of that shitty model over here.
So that model was more just to kind of show us.
Yeah, what I really wanted to show you is the connectivity of looking at just a few different elements, right? So that we can use VA to do this, right? So you go through and I generated nodes. I could draw areas, I could draw plates, right? If this was a slab on grade for you guys in the educational version, you can't auto mesh the area, right? I would draw an area and then I'd draw plates underneath it, right? Basically the same plane. And then you could change what type of pressure you had on the slab. If you were doing a slab on grade, say in a big warehouse, right, and you had different live loads in different areas, right, those areas would allow you to easily change those live loads, get different things, and then those areas would then load your plates, okay? But I really was just trying to highlight just these different tabs in VA, right? So we have our model view, for instance. If we highlight these, we're going to delete this whole thing. Oops. Now it should run. Nope. Oh man, this thing's been really weird this morning because I've fixed everything and it still won't run. I'm going to draw this again. Drew an area, I auto meshed it. I'm going to say it's 75 square inches. Concrete has thickness. Weird, why isn't it doing that? It keeps doing it this morning. Because I only have gravity loads.
What's your deadline for this?
It's just 1 kip, 10 kips. We'll put it 1 kip, I guess. It still should be totally fine. I had results before I walked in here, so. This is the beautiful part of this, right?
Did you release something when you were showing Elias?
Oh, Elias, did you screw us up?
No.
On this guy? I don't think I did. So we'll talk about this when we talk about like troubleshooting models, but a lot of times the easiest way to do some of that is to overfix a model and then work yourself backwards, right? So I could go through and we could fix every one of these nodes and then come back through and try and, well, I'm just gonna do that right now because I'm not gonna worry about this guy. Fix every one of these. Now it runs. It's a beautiful thing. All right. So when you run a model, these are all the local coordinates, which is stupid. Should get rid of that. But again, that's another, like, so we get, Adam wouldn't give me the most recent version of this, right? Give me version 19 or 21 right now, right? VA 21. Right. So you go into the results view. We messed around with this a little bit on Monday, right? In the results view, it gives you all sorts of information relating to the forces, right, and displacements in our element. This is the meat of what the analysis does, we want displacements, we want forces, right, moments. From there, we can calculate stresses based on the area of our member. We didn't really talk about this too much, but when we go to model, right, we did talk about this picture view, right? So that makes us feel pretty good about the scale of things and what things look like. If you want to figure out what type of shape, right, the homework for, I guess, the exam, right, you're gonna have to figure out a shape, right? You can add what's called a custom blob. Custom blob gives you area, moment of inertia, just really gives you really the bare bones of the parameters that you would use, right, to analyze something with respect to just its stiffness, right? Right. These.
I was looking at, but it says like it comes with many limitations.
There's
Blobs
second
are
class
second
citizens and visual
So I
analysis
made a
with many
blob and I was like,
limitations.
ooh, there's
The
second
limit.
class. Like, I don't know about this. So
Well, that's where you have to sit back and think gut feel, right? All you're really wanting VA to do is calculate displacements and forces for you, right? Right? And stresses. And in order to do that, it needs I, it needs A, right?
I want no second class citizens.
Right. So in this case, you could do a custom blob. It would have some dimensions to it. If you wanted to do something more than that, you could go into Shape Builder. You could build a shape. Okay. You can do standard parametrics, which essentially just allows you to do all different, just general shapes. Okay.
Download Shape Builder.
You can download Shape Builder. Then you can go through, right, the database, which just incorporates kind of all of your lock stock shapes, right? Whether you're in wood or aluminum or cold form steel, dealing with cables, right, rebar, stuff like that. The big one is steel sections. So if you wanted to design this moment frame out of wide flange sections, you might do a W16 by 31. You might do whoops. Database. I'm gonna make this 14 by 120, man. So, as I mentioned, picture view is beneficial here, right? If you were designing a moment frame, you would want the strong axes, right? Maybe you don't, right? If you're doing an ordinary moment frame, you don't have to. But in this special moment frame case, you're gonna have these strong axes to strong axes. This allows you to verify that, right? You can rotate each one of these members. So when we go to the model view, right, we're in the model view, we can look at this. We can rotate this member. We can change its action, whether it's two-way, right? And this is with respect to axial forces. Two-way, do compression or tension. One way, if you were doing a cable, right, that'd be beneficial. If you were doing, say, tension only, you might be able to do compression only. Concrete would be one, something that's very brittle. You're assuming it's just going to crack apart if it goes into tension. Type of framing member it has, whether it's a beam or a column or a brace. Okay. This relates back to areas and defined area loads and how the areas distribute loads. A lot of times areas will not distribute loads to braces. Okay. This also helps define when you go into, we'll do in a second, when you go into the design tab. Right, defines what type of member this is, which defines what type of checks you'll do, right? Steel design, you have chapter E or chapter F, right? Compression versus flexure. You would want to look at those. You can also look like offset coordinates, right? Basically moving this member with respect to its local coordinates, right? Which would then change the stiffness. We talked about, I think I drew a little picture up here of a concrete on metal deck, right? That's between joists, and the fact that a lot of times we look at that as a composite member together. So we're going to put headed anchor studs there. Well, then you're going to look at a composite member. Well, a composite member is going to have a lot more stiffness to it. So you might, in some cases, want to offset that member in order to incorporate that. Especially like the member you might want along center line, but you might want to make sure that slab's sitting on the top of the beam. So it allows us to do all sorts of stuff. Semi-tapered, semi-rigid connections, right? We can do linear, all these different stiffnesses with respect to rotations or translations. So those are the big ones. That's the material, right? You can create your own material, you can pick all these steel grades, timber, glue lamps, all of that stuff on the model tab, right? It also allows you to, right, in this project manager tab, allows you to filter things on and off. Some of the things you might be interested in would be like local coordinates. This allows us to relate back to, okay, when they're giving us an axial force, that direction of that axial force, positive or negative, well, it's all relative to our local coordinates, right? And that all comes back to the way you draw your members. So those are always critical things to see. If you wanted to, you can isolate members, you can do like highlight view. So now when you've got that member selected, if you have a very complex model, it's nice to just be able to see that one thing. A lot
How
of
does your,
viewing opportunities.
The
Yeah.
cantilever column have blocks at each node?
Because I just fixed all of the nodes so that this thing would run.
oh, and that's just how they,
Yep, that denotes, that shows or depicts a fixed support condition in picture view. Right? If I take that off, then it shows it based on these resultant or fixed arrows. Right? All right. So we have, say for instance, we have this frame. We decided to analyze it. It gave us an analysis, gave us the displacements, right? This is our deflected shape. We can do result filter. Right? Some of you guys, I got mad at you about the size amplification factor in your code, right? Well, VA does a size amplification factor because you might have very, very large models, right? Where some members are not going to displace very much, and we might want to see that, okay? Or we might not have very much displacement in general in structural engineering.
And that changes very depending on different things.
Oh, I don't think you can.
Which is one.
That's it? That can't be right. Okay.
Is there a reason why when you use weightless steel, still shows a deflection, gravity deflection from it until you turn off include dead load analysis, but it doesn't actually load the beam at all?
Yeah. Look at this. No, but I'm interested now. So you're saying if I do,
Yeah.
well, I'm going to do both of these. Come on. So if you're saying if I go through and I,
Go to material.
it's in general, right? I thought it was. Weightless steel.
Then take away your dead load.
Oh, take away? Well, you saying that now it still does it?
If you took the dead load off of it, so it's
Oh,
just
yeah,
the
yeah, yeah.
dead load that would be
Just the self-weight?
Self-weight, yeah.
All right.
What?
No displacement. No displacement,
That was
man.
not working for you.
Huh?
That was not working
Yeah,
for
you're
you.
doing something wrong. You're doing something wrong. Which,
Like,
it's
what's
good
the
that
loading
you
if
stepped
it's
into
not
it
doing
and then
that?
you're like, shit,
That's
it has no
wrong.
weight.
Yeah.
There shouldn't be any displacement. Hopefully you didn't just say, oh, whatever, I'll just
No,
continue
I
on.
just did a double. I turned it off and I did weightless.
Okay. That's great.
For when you had the plate one, if you had it just like 4 individual plates, then you make them visible, would that work?
Yeah, right? Because you are going to then capture all of the nodes that I generated, and they're going to be attached to something that has stiffness to it, which are the 4 plates. And yes, that should work. So, since we had to entertain Aaron's request there, oh, it's still weightless. Back one more. Okay. So we got results. We can change, right? So we can still do model filter. We can show the displaced shape. We can unshow the displaced shape. There's a lot of options here. Okay, it just comes by time, right? You got to spend some time looking at this. Some of the results, right? So we can do member results. If we have plates, it allows us to do plate results, right? So we auto mesh those plates over there. So we can do all sorts of internal forces, stresses, displacements, right? DZ local, that'd be the out of plane displacement, right? MZ. One thing to be very aware of is the sign convention for plate results. So we have, you guys have not taken plates and shells, but in plates and shells, you spend a lot of time going through the coordinates and how forces are delineated in plates, okay? With respect to, if you have a moment in the x direction, it's the moment in the x face, right? Not the moment in the x, like across the x-axis, if that makes sense. Like if you sliced this plate, I can't do it as well as Stordahl can. The wizard, right? So we go model, we go to plate elements. If I was originally looking at this and I said, I'm gonna look at the moment on the x space, right? Or moment in the x direction, I would immediately think that I'm thinking about the moment about the x-axis, right? Well, if you do m little x is actually the moment on the x face of the plate, right? Of the local coordinates. It can really fuck you up, okay? So I printed this shit up. It was in my office all the time because I was always getting it confused, okay? So all of these things can matter in a big way, right? With respect to results. And so when you're going over there and you're picking these results, you want to make sure, right, for plate results, we did m little x, local. It's going to look at on the x face, okay? Which it gives us nothing, which is weird.
Why is it showing triangles like that? Are
Those are each of the meshed plates.
so there's
What's
straight
the
up go
difference?
almonds?
Yeah, like why does it create triangles instead of rectangles?
Because remember we went back in VA, instead of having two different plate elements, now they can just have one plate element, right? It's an almond triangle plus the thick thin, right? It's a mesh of both of them. Because you can go through, and if you went through the model view, and we selected this guy, and we generate plates, right? And then we have this little option here that says membrane only. And as I mentioned, right, we have two elements. We have the almond triangle, and then we have that thick thin plate, right? The thick thin plate gave us degrees of freedom with respect to out of plane stiffness, right? And then the almond triangle gives you everything in plane. And so if you click this button, membrane only, it deletes all the degrees of freedom that we would have to have the out of plane, or that thick thin plate. And then all we would really have is the almond triangle, okay? And if you click that button right now, I have out of plane forces on this, it would not run.
But it doesn't do those 4 almond triangles in one plate like
No, so
usually
it
when
does,
you
right? So I
generate
drew an
plates.
area that was a
Automatic
rectangle,
filled with
and then it creates a bunch of triangles. We went through the notes on condensation, right? Where if you had a rectangle, you could essentially create another node at the center of it, right, the geometric center, and split it up into 4 plates, and that's what VA does, so that it doesn't have to develop a different element, right? Because you can't have a 4-noded almond triangle, right?
Right, but you
Because
can
you're
have-
adding degrees of freedom. But you could create a rectangular almond triangle by creating 4 triangles that create a rectangle.
Right, but it just shows, I guess, triangles instead.
Because that's what it's developed.
Normally every time you make a plate, it's like the 4.
This is an area that's generating plates of the size that you specified right there, and then it just fills in the exact number of plates that'll fit with each that size. You had just a plate like we did on the other one, and then you split them, it would look totally
Yeah.
different. And then that's when.
And then
on the wrong
internally,
plate,
it would do the 5th node separated into 4 plates.
For a plate, you would do.
Yes.
How do
That's
they
what VA is
determine,
doing
like,
on the
how to
inside.
lay out the triangles?
So that's, like, it's
They
really.
look really random.
Yeah. So you can go into these advanced mesher options, okay? And there's all sorts of methods that
Wow.
VA is using in the background to decide how it makes that mesh happen.
We don't have that in educational perspective.
No, you don't have the ability to take an area and make plates out of it. I don't think so. So in your case, you would, if you were modeling a footing, we'll get to at some point, right? You would model this footing, and then you would want to refine the mesh in such a way that you would get convergence of your results, right? If you were looking for mx, right, m little x, the moment on the x face, right, local coordinates, you would be looking at that, refining your mesh and making sure that, it's getting to some sort of value, right?
So
So back to the almond, the thick, thin, and like the CST, those are three different
Elements.
plates that give you different elements that give you different results.
Yes.
So you got in-plane, you got CST, you got almond, but the almond gives you an extra degree of.
So the CST and so the almond triangle and the CST element are all relative, or all looking at in-plane
stresses.
behavior.
Okay.
CST you can just throw in the trash, right? Because it's just like a step to get to the almond triangle, which is better in like all
Well, don't they
ways.
use CST elements in a lot
But
of
yes,
other
it depends.
applications?
It depends on the result that you're looking for.
Right, then it's like okay, but like still the almond would always be superior.
I would think so, but I'm sure there's people out there that would argue the other way. That means because like
CST guys that
yeah, the CST guys out there. That's awesome.
Then the thick thin is a totally different plate that's only looking at bending, out of plane bending.
The thick thin one.
Yeah.
Yes, just looking at out of plane bending degrees of freedom, right? It's adding the translation or the movement out of plane of this footing, right? And it also gives us the rotation for bending stresses, right? Rotation about the plane axes.
So it's like adding, like when we added our truss shape functions onto our beam shape functions instead of.
Yep,
getting both.
that's exactly what you end up doing, right? Because you're gonna have shape functions that are associated with degrees of freedom that the almond triangle didn't have. And so now your matrix just gets larger based on the degrees of freedom. Because like in this case, we have 3 degrees of freedom with respect to translation of this node, and we have 3 degrees of freedom with respect to rotation, right? So we've got 6 degrees of freedom that's possible for each one of these nodes. And remember from the thick-thin element, they also, internal in VA, there's a rotation of the global of the entire plate in 2 directions also that is taken into account. But that's all based on the nodes, degrees of freedom. So yeah, a lot goes into this, Greg. You can like tell it the minimum angle for that triangle, right?
Yeah,
And
that's great.
you could override the maximum angle. You can figure out different methods for the triangulation, like how it's doing it, right? I have honestly never messed with this. Because I mean, in reality, we're all looking for a certain result for a certain like design. Right? As I mentioned, if I was designing the frame members, the beams and columns in that frame, I was assuming that the base plate was fixed, I'd just fix the node and move forward, right? But if I was looking at soil interaction and I wanted to know, right, how the overturning of that frame is now going to affect the footing, then I would want to incorporate the footing. And I'd want to incorporate the stiffness of the soil underneath that footing. And in the end, I would be refining my mesh until it got to some level of convergence. I was comfortable with the idea that what I had modeled, one, was accurate to my interpretation of the real world, and then on top of that, those things aren't going to change drastically if I continue to refine my model to the point where I'm under-designing or over-designing something, right? Like a footing or a beam or a column. We are ready to 50. Wow.
Do you want a copy of our VA and our MATLAB code?
No, I was supposed to get to that point, right? So we've got design view. Well, we can go to report view, right? And there's a lot of options in VA as to how we report. Essentially, you can double click on this or drag it over here, and you can generate a big report off of it.
Like that's what you want, is that what you're saying?
Well, I want to see something, right? I want to see, make sure you model
It's
something.
not like screen captures.
Oh, screen capture would work too. Yeah, you can cheat, do that.
Cool,
Yeah,
actually.
for sure.
That's what I'm
Snip
all
tool.
about.
Show the
Yes, sir.
results. On the final thing, on the last part where we're using mechanics to draw internal diagrams.
Yeah.
If you go over, there's a member graph. Is that cool to just copy what the member graph says, or do you actually want to see like little hand calcs of cutting sections along that beam?
I want to see it in code.
Oh.
I want to see it in
They said
code.
we could draw it.
Yeah,
Yeah.
it's you. I want to. It
said
needs to be
use
sketched,
free
but you need to
diagrams.
get that. Yeah. Well.
Because it's
You said
indeterminate
that.
if you don't.
You said use mechanics.
I thought you meant like you want us to like cut sections and like move along like we did in mechanics materials like 201 or whatever it was.
That would be mechanics, right?
Yeah.
And then you need to draw. And then do you, like the last thing is to, yes, go back to VA and relate it back to VA.
Well, yeah, you gotta check it.
But like, you want the work of the mechanics is what I'm.
Yes, yeah, for sure, cause that's the part that is keeping it separate from just going to VA and just like putting a piece of paper over there and sketching over the top of it, right?
Yeah.
I wanna know how you could get those curves.
Who's that determined?
What's that?
Oh, but no, actually.
Okay. It's not indeterminate.
It isn't like.
It is in
If
an
you
overall
pull it-
global sense, if you like looked at it overall,
Or
but
if you
you've
tried
gone
to
past
pull
that
out-
already.
If you tried to
Yeah.
pull out the section and consider one like.
'Cause you can break it at the node,
Then it would be
and you know that-
Is what she's saying.
Yes.
My point is this
Move
like
on.
a hand calc thing, or do you really want that coded in?
You don't have to code it in. The question asks for a sketch, right? But in order to get there, you need to base it off mechanics. So I would like to see how you got to drawing something, right? Okay, good. I will be walking to my office.